So what we're going to do now, we're going to look at ideal transformers. Now, an ideal transformer is one that does not lose any power uh, within the transformer itself. In other words, the power generated on the primary side must equal to the power that is generated or produced on the secondary side. And so let us look at some results of that. Now, as we've mentioned, the flux is conserved in a in an iron core like this, or at least in an ideal transformer, we say that the flux is definitely conserved. And so we know that multiplying the flux by the number of turns on each side, Np or Ns, gives you something called the flux linkage, which we know is N phi, and we know that this flux linkage is directly proportional to the amount of EMF that you can induce, or at least the rate of change of this flux linkage is directly proportional to the EMF induced. And so what this means is that there is a linear, or should I say a direct proportion relationship between the voltage Vp over Vs to the number of turns Np over Ns. And so this is your fundamental transformer equation. And so by adjusting the number of turns on NP and NS, you can decide how you want to scale your primary voltage to become the secondary voltage. And so there is an interesting implication of this in ideal transformers. Now, if PP equals to PS, then of course that implies that VP IP, the current that is drawn here, must then equal to VSIS, which is the current that you have on the secondary side. And so rearranging, you have VP over VS equals, of course, to IS over IP. And so I can extend this transformer relationship a little bit more and show that the ratio of the currents, at least for ideal transformers, is inversely proportional to the ratio of the turns. And over here, this is how we then mathematically describe the functioning of an ideal transformer.